Okay, we're moving over to page 87 of your book, and we're going to look at how we can connect these sequences that we've been talking about with series. So a series is adding the terms of the sequences, where a sequence was just a list of numbers that had a pattern or some sort of relationship. So when we look at number 1, it says to fill in the blanks for each sequence. So when n equals 4, we have, or n equals 1, we have this picture. N equals 2, 3, you can see that it's 3 by 3, 2 by 2, 1 by 1. We have a 4 by 4 square. And so if n equals 5, we'd have to go 5 by 5. And so that would be a total of 25 squares in there. So let's see, it says, is there a formula? Let a sub n represent the number of unit squares in the nth term of the sequence. So we know that the first term had 1 square, the second term had a total of 4 squares, the third term has 9 squares, and the fourth term you could see there were 16, and the fifth one there were 25. So you can notice that these are actually talking about all the square numbers. So a sub n would be with n on one side, n on another side, and so that's going to end up being n squared. When you look at number 2, we have only a few terms listed, 4, 6, 8. That sounds familiar. 2 sounds like a good number there, 2, 4, 6, 8. Oh, and then 10. And so what's happening every time for this sequence, you can see it's adding 2, adding 2, adding 2. That's actually called the arithmetic sequence, which we just were talking about. And so our first term we saw was going to be a 2, and then a 4, and then a 6, and then it wants to know the nth term. Well, let's think about how these terms were found. When I'm on the first term, well, that's just the first term, but to get to the second term, I needed to add a 2. To get to the third term, I added 2 2's. To get to the fifth term, how many 2's do I have to add? 1, 2, 3, 4. So it's always a 1 less than where I started. So if I want the nth term, well, I got to know my start, which is 2, and we sometimes will write that as a sub 1. And then we're adding a whole bunch of 2's, and it's going to be 1 less than where we are. So if we're at the nth guy, that's going to be n minus 1 of those 2's, where 2 was the common difference. So again, to see like how it works here, like we can just see that the third term is 6, but we could have found that by saying, well, I know that the third term is found by looking at the 2, which is the start, and adding, well, 1 less than where I am, so adding 2 2's. And that is equal to 2 plus 4, which is 6. So that formula is fitting. We could simplify that by distributing that through, so we could have like 2 plus 2n minus 2. Well, really that's just 2n. So the nth term is really just 2n, which should look familiar. That's a little multiple of 2, or the multiples of 2, which is what we have listed here. For number 3, we have 2, 4, and then 16. So this is following a little bit differently. If I look at the relationship here, that looks like I add 2, but then if I add 2 again, that's only 6, add 2 again, I'm only at 8, and that's what that sequence right above was. So to get to 16, I gotta do a little bit more. I'm gonna be doubling. So 2 times 2 is 4, times 2 is 8, times 2 again, that's 16, times 2 again, that leaves me to 32. So this time when I'm doing that multiplication, that was our geometric sequence. Oops, it already says sequence. All right, and so again, we know that our first term here is 2, and then 4, and then 8, but it wants to know the nth term. And so if I'm looking at, let's look at this fifth term here. If I want to get to my fifth term, I would need to know my start, my A1 guy. And then because it's following this pattern, since it's geometric, that means that it has a whole bunch of 2's multiplied. And it actually has, you could see, 4 2's being multiplied by the time I get to the fifth term. So I could say that my fifth term was found by starting with a 2, then multiplying by 2 4 times. 2 times 2 times 2 times 2. So if I want to write in general, then that's going to be, I start with a 2, then I multiply by 2. So this is the starting term, and this number, we call that the common ratio. And we're going to need 1 less than where we are, so we'll write that as n minus 1. And so we could combine this together using some rules of exponents, because there's like a 1 on this 2. We could add those, so this would be 2 to the n, really. So we could say the nth term is 2 to the n. And again, both of these should look really familiar. The first one was kind of mimicking and looking like our linear equation because it's growing by the same constant 2, or like going up 2 over 1. This guy is doubling every time. So remember, this guy was more looking like our exponential function. All right, we're going to skip over the creating and move over to see what happens when we start adding these terms. So the first part here, we have an arithmetic sequence. I'm going to fill this back in. 2, 4, 6, 8, 10, keeps on going. And we want to see what the sum of the sequence is. And we're going to have a new notation for these partial sums. So when you see S1, that just means add the first term. S2 says you're going to add the 2 terms. And so on. These are partial sums. You're going to add the first 3 terms all the way to, we just have S5 here. So one thing that we can do to kind of see, well, how could you add this quickly? We say 2, 4, 6, 8, 10. If we write it the reverse way, 2, 4, 6, 8, 10, what happens is this is going to be 12, this is going to be 12, and we get a 12 and a 12 and a 12. If we're adding 5 terms here, we're going to have 5 of these 12s. And so if we want to try and calculate the S5, well, 2, 4, 6, 8, 10, 2 plus 4 plus 6 plus 8 plus 10. Like, we can sit here and add that, but if I asked you for a larger sum of the sequence, it would get a little bit harder. But if we notice this pattern about the first guy plus the last guy is 12, and I noticed that I would get all these 12s, what I'm doing is really adding S5 twice. So I know that I could do 12 because that's the sum of the first guy plus the last guy. And there are 5 of them. But I need to divide that by 2. So this can't be 60. It's going to be 60 over 2, which is 30. So it has to be half. And if we actually just add 2 plus 4 is 6, plus 6 is 12, plus 8 is 20, plus 10 is 30. It worked. So why would we want to do that if we can just like add the numbers together? Well, sometimes you'll have a larger sum to do. You'll have to find something like S40. That's going to be 40 things that you want to add. But using our pattern here, if I was going to add 2 plus 4 plus 6 all the way to the 40th term. We got to think about what that would be. The 40th term. Well, the 40th term would be found by knowing the first guy, right? We're saying A40. We have to know the first guy, and we know we're adding a bunch of 2's. In fact, we'll have to add 39 2's to that. So I know my last guy, let's see, that's going to be a 78 plus 2. That will be 80. So I'm going to keep adding all the terms all the way up to 80. Well, using the pattern that we saw over here, if I were to set up 2 plus 4 plus 6, blah, 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 all the way up to 80, and then we reverse that, 2 plus 4, right, this would be like a 78, all the way down to 80, you can see we're going to get 82's, a bunch of them in there. And how many are we going to get? Well, it was the 40th term, so that's going to be 40 of those. So a quick way to add those terms is to say the first guy, which was 2, plus the last guy, which is 80. That's a sum of 82. We're going to have a whole bunch of those. But we're getting double the amount, so we're going to take half of that. And the number of terms we're going to get is 40. So our sum here will be 82 over 2 times 40. Which will equal 1640. So then what we can say to find the sum of n terms is to take the first guy plus whatever the last guy is. I'm going to add those together. Divide it by 2, but times that sum by how many terms there are, which is n here. And that's a fast way to find the sum of any arithmetic sequence if you want to know the first n terms added up together. So let's see. The next sequence we want to look at is our geometric sequence. So we're looking at 2 times 2 is 4, times 2 we got 8 again, times 2 is 16, all the way to 32. Okay, so we know the first sum, the first digit, that's 1, and then we're going to add like 2 plus 4, and then we're going to add 2 plus 4 plus 8, and 2 plus 4 plus 8 plus 16. But again, when you want to start adding larger numbers, it's going to get a little more complicated, so we want to have a formula for the sum of the first n terms. So what we're saying here is that we want to look at, well, Sn would be whatever our first term was, but our second term would be a1 times whatever that common ratio is, and then we're going to get a1 times the r again. So r times r, that would be r squared plus a1 r to the third plus da 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 da. You're going to keep doing that all the way to that nth term, which will have one less r than where we're at. And so something kind of interesting is that if we take that sum and then minus, let's look at r times that sum. Well, let's look at what r times that sum would be. So every single term here would have to multiply by r. So that would be an a1r, an a1r squared, an a1r cubed, a1r to the fourth, da da da, all the way a1r. If we multiply by another r, that would put us at an n there. And so if we subtract the first sequence here, or series, minus that, look what's going to happen. If we're minusing, these would cancel. All the diagonals are going to cancel. And so all we have left then, we have that Sn minus this Rsn would equal a1 minus a1 r to the n, this last guy. Okay, that's great, but what does that mean? Well, I want to find a formula for Sn, and so over here on the left side, I have a Sn I could pull out. I'll have 1 minus r here equals a1 minus a1 r to the n. I could divide by 1 minus r. And so I could write that Sn is equal to this a sub 1 minus a sub 1 r to the n over 1 minus r. But even better than that, sometimes what we'll see is that they take the a1 out. So a1 factored out would be 1 minus r to the n all over 1 minus r. And so that is the formula for the sum of the first n terms of this time a geometric sequence. So you don't have to memorize these sums or these big fancy equations, but it would be nice to understand how I kind of prove that to you right here. But we also want to be able to use them. So I have one more sum that I want to show you, and that is when you want to add up some terms in a geometric series, but it's an infinite sum. So if you look at what we have right here, we have a list of numbers, 1, 1, 6, 136, and the dot, 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 dot means it doesn't have an end. So if you look at the last thing I just showed you, it had dot, 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 but then it had endings. This was like the first term, the first 2, first 3, first 4, first n terms. I wanted you to add those together. So up here, we're saying an infinite number of terms. And so what happens is you can actually add an infinite number of things and have the sum be a number. And so what does that mean? How does that happen? Well, if you look at this series that we have, the sequence is geometric because each time it's timesing by 1/6, timesing by 1/6, timesing by 1/6. And so our r would be 1/6, and also to notice that our terms keep getting smaller and smaller and smaller, because to multiply by 1/6 really means dividing by 6. And so if we said that our formula for the nth term looked like that, or the nth sum, let's think about what happens as r to the n, if you have r to the n, if n is getting big, so n is, sometimes we'll say like going to infinity, it's getting big. What's happening to that value? Well, if it's a fraction, it's taking a sixth of a sixth of a sixth of a sixth of a sixth, getting smaller and smaller and smaller and smaller. It's actually getting close to zero, getting close to nothing. If you keep dividing something up, it's going to get smaller and smaller and smaller. It's going to close to zero. It'll never actually be zero, but it'll be the teeny tiniest number. And so if that's going to get close to zero, look at what we have. This r sub n will go to zero. So we're just going to have Sn equals a1 over 1 minus r. And so as long as that r is going to zero, so here's a fancy way of saying that. If r is a number less than 1, like a half or a third or a sixth, then the sum for an infinite geometric series will be the first term over 1 minus r. And so I skipped over at the beginning, but you can see that when I have that first sum, it's 1. Okay, that's fine. But then I'm going to add 1 plus 1/6. And when I add 1 plus 1/6, well, it's 1 and 1/6. But it's going to be 1.2. And then if I add 1 plus a 6 plus a 36, I'm going to take that same number, but add in 136. It's not going to affect me so much. It's 1.19. And so you can see this number is getting to be like, it's close to the same number. And so let's see what happens if I want to keep adding 1/36 and then whatever, let's see, 36 times 6, 1 over 2/16 and so on. Let's try and use this formula. So the sum is the first guy, so that's 1, over 1 minus the 1/6. Well, this is really 1 over 5/6, which is going to be about, so 1 divided by 5/6 will actually be about 1.2. So these numbers that we keep adding here, as you start to find like the fourth sum, the fifth sum, they're just getting so small, the numbers that we're adding, so it's really sticking around the same number, 1.2. And so I wrote approximation because I rounded this number, but it actually ends up that it's exactly 1.2 because I didn't have to round. Let me fix that actually. And punch that into your calculator to make sure that you get the same thing. It is actually exactly 1.2. So that's going to be the sum of our infinite geometric series. Now, if our r is greater than 1, we say the sum does not exist. And you should think about why that happens. Give you a minute to pause on that. But the reason why that can't happen is because you would keep getting bigger and bigger and bigger and bigger. R to the n would just get big, so going to infinity, not 0, so you can't find the sum. It just keeps getting bigger. So for number 7, giving you a chance to find a sum here, we have -3 plus 1 minus 1/3. This is multiplying by -1/3 each time. And if you're not sure how to get that, remember you could take like the second term, divide by the first term, then the third term, divide by the term above it, and each of them is getting me that -1/3. So I know that's my r. And so I know I'm going to get smaller. Even though I'm adding and subtracting, I'm adding and subtracting a smaller and smaller and smaller amount. So to find my sum, I just needed to know the first guy, that's our a1, divided by 1 minus that r. So that's -3 over, we have 1 plus 1/3, that's really -3 over, that would become 4/3. You could divide that on your calculator, or you can multiply by the reciprocal if you like that better, but it's going to be -9 over 4 is our actual sum. Adding up an infinite number of terms to get a finite number. Kind of crazy. Okay, so to kind of finish this off, the nth term of an arithmetic sequence, if you want to find just the term, what we said is that you look at the first guy and then you add on 1 less than when you're at of the common difference. To find the nth term of geometric, you got to know your first guy, but then you're multiplying by that common ratio 1 less time than where you're at. And for our sums, for arithmetic, you add the first guy plus the last guy divided by the 2, multiplying all of that, sometimes we'll put that in parentheses so we see that, multiplied by the number of terms there are. For the geometric, it's going to be a sub 1 times 1 minus r to the n over 1 minus r. And then again, if we think about infinite, and as long as our r is going to be less than 1, we're going to just have a sub 1 over 1 minus r. And so what you should do next is use all of this information to try and solve the remaining problems down below. We don't have problems in ALEC, so I want to give you some time to try these. So make sure you push pause before you check in on these. This is going to be your homework for this lesson. So pause it and make sure that you try 1 through 4. Now that you've tried them yourself, we're going to look at the first one. It wants us to find the sum of the first 75 terms. So we're looking for S75. We need to figure out what kind of sequence this is. So we're looking 9, 12, 15. So that's adding 3 each time. So for adding 3, we know that we're arithmetic. And if you're arithmetic, you need to be able to add the first term plus the 75th term. We'll divide that by 2, then multiply by 75. We know the first term, but we don't know the 75th term. We got to figure out that 75th term. Well, the 75th term here will be equal to the first term plus a whole bunch of those 3's, and it'll actually be 74. So it's 1 less than where you're at. So if we take the 74 times 3 plus the 9, it ends up that's 231. So our sum will be 9, because that's our first term, plus the 231. We'll divide that by 2 and then multiply by 75. So 231 plus the 9 will be 240. Divided by 2 is 120. Times 75 will be 9,000. That's our sum of the first 75 terms. All right, for number 2, let's see what's happening here. We have a 2 and then a -1 positive. As soon as I see positive, negative, I know it's geometric, and it's going to have a ratio that's negative because it keeps changing sign. So to find that ratio, if you're not sure again, you can take the second term divided by the first term, or the third term divided by the second term, but they're both getting me -1/2, so I can see that as my common ratio. And it wants me to find, it says ... so it doesn't end. So that's an infinite geometric sequence here. And if I want to find the sum of that, I need to just know my first term over 1 minus r. So my first term is 2. I'm going to divide by 1 minus that -1/2. That's 2 over 1 plus a half, 2 over 3/2, which will equal 2 times 2 over 3, which will be 4/3. All right, so the next one, it says find the sum of the first 6 terms. So we know we're finding a finite sum, and let's see what's happening. 10, 2, it doesn't look like they're adding anything, so let's look for a ratio. This must be geometric. So 2 over 10, well, that would be a 5th. And let's check the third term over the second term. 2/5 divided by 2, that's also 1/5. So we're going to take the first term times 1 minus r to the 6th all over 1 minus r. So our first term is 10 times 1 minus, we're going to have to take 1/5 to the 6th power, and this will be all over 1 minus the 1/5. So 10 times, I'd want to figure out that parentheses first. You can punch it all into your calculator, but I find that a lot of students make some mistakes that way. So if I find out what 1/5 to the 6th power is, and then that's going to be 1 minus 0.123412346 I'm going to multiply that by 10 and then divide by, 1 minus 1/5, that's 5/5 minus 1/5, that's 4/5. So I'm going to divide by 4/5, and it ends up that it's approximately 12.49, so about 12.5. Which kind of makes sense if I just kind of go back at the first term's 10 and 2/3 my 12, and then 2/5 is 0.4, and then they're going to keep getting smaller and smaller, so that sounds about right. Okay, I got one more left on here that you should have tried. 3 plus 6 plus 12. Let's see. It's going to be 3 and then 6 and then 12 and then 24. This is doubling each time. I don't see anything that I'm adding. So then that's going to be geometric. And my R is 2. Now this time I noticed that it's ... but it's an infinite series. But since R is 2, it's just getting bigger and bigger and bigger and bigger, and so the sum does not exist. And that's what we got.